In this video, I want to take a look at the gradient and show how that helps us to find tangent planes to surfaces that are described by z as some function of x and y. So we've actually done this already, and I'm not using the gradient, but back we talked about tangent planes and how did you find them. If you remember, the way we did it was we used the partial derivatives to find two vectors that were parallel to the surface. We then took a cross product to get a vector that was perpendicular to the surface. And as I recall, that vector that was perpendicular had the partial of f with respect to x was the first component, the partial of f with respect to y was the second component, and minus 1, I think, was the third component. And then we used that normal vector to be the normal vector to the plane, and so it was the coefficients for x, y, and z in the equation of the plane. Anyway, let's see how we can do this using the gradient, because the gradient is really good at giving us a vector perpendicular to a surface, right? Yeah, perpendicular to level things. So suppose we want the equation of the tangent plane to the surface z equals f of xy at the point xy equals x0, y0. I want to take this now and rewrite this equation as essentially subtract the z over to the other side, f of x comma y minus z equals 0. And then think of a function of three variables, g of x, y, z is this left-hand side of the equation here, f of x comma y minus z. The thing is, the gradient of g will be perpendicular to the level surfaces of g, but one of the level surfaces of g is the surface we want, right? Because this is g equals 0. We have the level surface of level 0, and I'm going to move over just a smidge so you can see the 0 there. So take a look at what the gradient of g is. Well, the gradient of g is a vector. The gradient of g is a vector whose first component is the partial of g with respect to x. The second component is the partial of g with respect to y. And the third component is the partial of g with respect to z. Now, look what happens when you take the partial of g with respect to x. Well, the only x's are the x's that are buried inside of this f, whatever that function is, right? So taking the partial of g with respect to x is the same thing as taking the partial of f with respect to x. This doesn't contribute to it at all. So the partial of g with respect to x is the same as the partial of f with respect to x. Likewise, the partial of g with respect to y, the only y's are what are buried inside of f here. And so that partial derivative is the same as just the partial with respect to y. Now, there's no comma z's anymore because f is only a function of x and y. Right? And then the partial of g with respect to z, well, the only z in here is the minus z, and the partial derivative of that with respect to z is minus 1. And so when you plug in your x0, y0, z0, of course z0 is what you get when you plug into there, you get fx at x0, y0, fy at x0, y0, comma, minus 1. This is exactly the vector we got before with the cross product. Right? And you may remember when I took that cross product, I had a choice of which way did I want to do it. I could have done, if I did it one way, I'd get one answer. If I did it the other way, I'd get negative that answer. And I chose a particular way because I wanted these to be pluses and this to be a minus. So we end up with that same vector. Now, this is remarkable to me because, again, thinking back to my days of learning this, when I thought about the gradient of f, I had the misconception that it pointed up the slope. It doesn't point up the slope, right? If the slope is here, the gradient is pointing in the direction of the steepest increase, but it's not pointed up or down, it's just pointed straight out. But it's pointed straight out at just the right amount that, I'm going to use the black pen here, so that black pen is telling me the direction of the steepest increase, but if I give that black pen now a z component of minus 1, it'd be just enough to make it perpendicular to the slope. Right? Because without the minus 1 here, just those two components, that's the gradient of f. But now the gradient of g has those two components with a minus 1, and it's perpendicular to my surface. And it can serve now as the normal vector for my plane. So here, let's do an example. Here is the function z is x squared minus xy, and I'm just going to do it at the point 2, minus 1. right? Here's f. The gradient of f would just be minus 2x minus y, comma, minus x, so partial with respect to x, partial with respect to y. G, of course, was just this function f minus z. And notice when I take the partial of this with respect to x, it looks just like it did up there. Take the partial of this with respect to y, you get the same thing as you did up there. And then the partial with respect to z is minus 1. Right? So these first two components, or the only two components for the gradient of f, are the first two components of the gradient of g. And now when we plug in the point 2, 1, negative 6, where did the negative 6 come from? Well, if I plug 2 and 1 in for x and y, then, sorry, 2 and negative 1, 4 plus 2 is 6. So the z component, the z value there is 6. You plug them in here and you get 2 and negative 1, so I get a 5 right there, negative 2, and then negative 1. So the gradient of g is 5, negative 2, negative 1. And the tangent plane is the z component plus 5 times x minus 1 minus 2 times y plus 1. And there is the surface. So this is the surface that we had. It's this sort of twisted paraboloid, hyperbolic paraboloid, whatever it is. Yeah, that's hyperbolic paraboloid. And the point 2, 1 is 2, negative 1 is up here really high, altitude of 6. But you can see that the gradient field that's drawn in there, this is not the gradient of f I'm drawing, this is the gradient of g, which is f minus z, is always perpendicular to that when it crosses. Again, it's kind of hard to see when it crosses, like this point right here, perpendicular, over there, perpendicular. Right. And so that gradient, partial f with respect to x, partial f with respect to y, comma minus 1, is perpendicular to that surface. Right. Now this surface that we have is when this is equal to 0, but you can look at, g is describing a whole bunch of surfaces, because g equals different constants gives you different surfaces. And all those gradient vectors, well, where the gradients cross the surface, they cross it perpendicularly. Okay? We were just interested in one surface here at g equals 0. And that would give us, that gradient field would give us normal vectors for tangent planes wherever we wanted them. So there you go. There's using the gradient to help you find equations of tangent planes.